All right, welcome back after break. Yes, as the intro screen stated, we are moving on into Chapter 8, Section 4, and we're looking at the z-test for a proportion. The z-test for a proportion. Proportion we denote by, as you might have guessed, we denote that by p. Okay, so let's talk about notation. For notation p, hold on one second. Screen doesn't like me for some reason. For notation, P is our population proportion. So the example that I keep coming back to is, the population proportion here might be the true number or the true percentage of the population that is going to vote for a particular candidate. And so what do we want to do? We want to try to predict what is that particular population proportion. In a hypothesis test, that is exactly what we're going to be doing. We're going to be making a prediction about our population proportion, P. For the sample information, we'll denote this by P hat. Okay, so just remind you that it's pronounced P hat, not fat with a P-H, but P hat. And that will be our sample. Sample, and I'll just put ditto for proportion. To compute P hat, you will take the number of people in your sample that have that characteristic that you're looking for, whatever it is, and divide by the total number of people in your sample. To get the other information or the other, let's say, the other quantities, the other variables that we need to use in our formula, we're going to be using not Q hat, not the sample complement proportion, but the complementary proportion for the population. So to compute Q, you just take whatever the hypothesized value of P is, and you do 1 minus that. Okay, so that's basically it for our notation, and that's pretty similar to what we've already seen. So now we'll move on into our important formula. This is how to get our test statistic. So the test value, I'll just write it verbally, is the same format that we always do. So it's going to be, it's similar to what we always do. It's the value out of the distribution minus the average or the mean from the distribution divided by the standard deviation and the standard error. So here it's not an average value, but we are looking at something. So that's kind of the point of that. It's our observed value. And then minus the expected value. And then that is all going to be divided by the standard error, which is basically just another way of saying the standard deviation. Okay, so there's some technicalities that need to be addressed. The sample needs to be a random sample. The conditions that are needed for a binomial experiment need to be satisfied. And then here's this thing. I'll just write it right here. In P has to be greater than or equal to 5, and N times Q has to be greater than or equal to 5. So that means we're going to need at least 5 successes and 5 failures. We can't test proportions that are, 100% or 0%, basically, or too close to that range. We're not going to get accurate results or readings on that. So let's get into what is that important formula. How do we compute the z-value? In this case, the z-value is going to be the observed value, so that is our sample proportion. We take the number of people or items out of our sample that have the desired characteristic and divide by the total number of items that we had in our sample. Minus P, so this is whatever that we are talking about. Let's just put a little note here. P, remember that's the population proportion, and it is the hypothesized population proportion. So that means that value is going to be the one that we keep referencing over and over and over for H subscript 0. And then also, again, we use that same exact value. We just use an inequality for H subscript 1. And then here in the denominator, this is the square root of the whole thing, P times Q. So we can just write it as PQ divided by N. And that's all underneath the square root there. So let's see, minute 7:50. Let's begin a quick example. So this will be the first example from chapter 8, section 4. This is example 8-17, and we're looking on page 454. So let's read and see what's going on here. Researcher claims that based on the information obtained from the Centers for Disease Control and Prevention, 17% of young people ages 2 through 19 are obese. To test this claim, she randomly selects 200 people ages 2 through 19 and found that 42 were obese. At alpha equals 0.05, is there enough evidence to reject the claim? Okay, so here, what is being told to us? Basically, the 2 through 19, those are just the ages of these young people. This is the subsection of the entire population of the United States. This demographic, this age group is the population that we're considering, right? And so the parameter, that proportion of the percentage of those who are obese is 17%. So we're basically given P is equal to 0.17. That's what we're going to be using in H subscript 0. We're going to say exactly that. We're going to say P is equal to 0.17, right? We're also going to need to know what is Q. So if P is 0.17, 1 minus 0.17, it comes out as 0.83. Okay. What else do we know here? We're going to be using a level of significance. Alpha equals 0.05. So that's pretty standard value. Remember, that's our default value. If they just say test the claim, or is there enough evidence to reject the claim, and they don't tell you an alpha, guess what? 0.05. There it is. All right. And then what else do we know here? Oh, we have to be able to compute p hat, right? So, how do we do that? Remember, it is x over n, and so here they tell us x is 42 and n was 200. So from that information we can compute our sample proportion. So let's go back through, just so remember, right, all of the steps, this 5 steps of hypothesis testing. So step 1 is we'll state the hypotheses. The null hypothesis, H subscript 0, is as follows. P, the population proportion, the true proportion of young people ages 2 through 19 who are obese, is indeed, as the previous study claimed, the previous statistic was 17%, so that's what we are assuming as the status quo. That's our null hypothesis. All right? Our research hypothesis, the alternative. What's the alternative here? What do we suspect the alternative might be? Well, we're looking at this and we're testing the claim. So we're suspecting that it's potentially old news and the true value is something different. So notice here, this is going to be a two-tailed test. So moving on into step 2, we have to find the critical values that define the critical region. I'm not gonna stress about that. We have to what? It's always a good idea to sketch the distribution curve. So here we're going to talk about this. Remember that when we have just a simple not equals inequality, then in the alternative hypothesis in H subscript 1, then that means it's going to be a two-tailed test, whatever our distribution is. And in this case, it's the z distribution, so I'll just write a little z there. Okay, and alpha is 0.05, so that means we have on this side 2.5%, and on this side 2.5%. And the reason I keep saying the z table is so nice, it's actually pretty nice because it's included as a part of the t distribution table. If you go to the t distribution table and you look in the column that corresponds to two tails, alpha equals 0.05, and you don't look at the degrees of freedom, you just go all the way down to the very bottom, you'll notice that that's the z distribution. That's letting the degrees of freedom approach infinity. And so then the t distribution, that family of curves, approaches toward the z distribution. You don't need to know all of that. All you need to know is at the very bottom, it shows us the actual critical z values that we all know and love. And if we don't remember them, then there they actually are, all in a handy-dandy place, and we don't have to go searching through the z table. So we have our critical values. Now, step 3 is we're going to go ahead and compute the test statistic. So remember, we always want to try to write that down from our memories. P hat minus P. It's always the sample information minus our population information. And then here, it's P times Q. So we always have something to put in for P because we always have some value that we're imagining, we're conjecturing about it. And that's not exactly the same as what we had in the case of confidence intervals. Exactly. All right, so here I didn't show the work, but 42 divided by 200 reduces down to 21 over 100, just dividing by 2, and that is as a decimal, old familiar decimal, that's 0.21. So our sample proportion, p hat, is 21%. The hypothesized population proportion, 17%. And then we're going to go ahead and pop in the values that we have for P and Q. So 0.17 times 0.83. And then inside that square root, we're dividing by 200. And then we'll hit enter on the square root. So I always tell people the square root starts you off with parentheses. So after you get done plugging in all of the stuff that you want to put into the parentheses, just close it off with that last parenthesis right there. All right, so anyway, speaking of the calculator, handy dandy calculation gives us 1.51 for our z value. All right, so let's go ahead and see where does that fall. 1.51. You know, the picture doesn't have to be super accurate, but it is right here, 1.51. It's lower than 1.96, so it falls outside of our critical region or our rejection region. So therefore, in step 4, we fail to reject the null hypothesis. And so then finally we have to summarize the results in words. Let's scroll there. Let's scroll up a little bit and summarize the results. There is not enough evidence to reject the claim. So here our claim was what? Basically, we had to substantiate the previous study. So we said we're not throwing away this statement right here, that P is no different than 17%. Okay, even though our sample proportion came back at 21%, based on the distribution, based on our sample size, that was close enough. So there's not enough evidence Remember, that's how it starts off every single time. You fail to reject H subscript 0. Anytime you don't reject H subscript 0, there's not enough evidence, da-da-da-da-da. And then you say whatever you wanted to happen in H subscript 1, you just say, well, there was not enough evidence to say that that was going to be true. So what we were saying in H subscript 1 was that it's not 17%. So there's not enough evidence to reject the claim that it is 17%. And so that completes our first example of a z-test for a proportion.